Okay, good morning, everyone. And I think I can hear you today. There shouldn't be any issue. Okay, how did the homework go? Do you have any questions while I wait for everybody to join in? Okay, so 11 and 17. Okay. Right, so we look very quickly at them. So yeah, number 30, I have to talk a lot about it. So number 30, we have to hold on to it. So number 11, it was a typical scenario, -1 to the k, to k plus 1, 1 to infinity. Okay, so that's really our series. And this is an alternating series. It means if we write up the term are going to be oscillating between positive and negative. So my k is starting at 0, sorry. Okay. It doesn't matter what k start, those will also alternate. So at 0, we have a 1, and at k equal to 1, I will have minus 3 plus 1/5. So we add and subtract all the odd numbers. That's really what we're doing, and so on and so forth. And in this setting, the AK, which is, as I said, in an alternating series, the AK are not the terms themselves. They are actually the absolute value of the term. These are the AK, which is 1 over 2k plus 1, only in the alternating series scenario. All right, so as this conversion, we check both conditions of the alternating series test. First, the limit of the AK is equal to 0. So first condition is satisfied, but we need two of them. We need to make sure that the sequence of the AK is decreasing. Basically, I want to make sure that those individual terms decreases when K increase. Now, in this problem, is almost clear that when K increases, the denominator increase. So the denominator is increasing. It means that the terms are increasing themselves. So when the denominator increase, 1 over the denominator is definitely going to decrease. So those are easy scenario, but let us make check. So we're going to check that the AK, the sequence AK is decreasing. Okay. So we have to verify basically in this scenario, because it's an easy scenario, that AK is always larger than the term after. So we have to verify that AK is always larger than AK plus 1. But let us see here. AK is, the denominator is 2k plus 1. The denominator here is 2 times k plus 1 plus 1. And 2k plus 1, sorry, is definitely less than that, because k is less than k plus 1. So when I'm going to flip them, this is going to be bigger than that. Okay, so we have to verify that every term is larger than the terms that comes after it. And AK, the denominator involved is 2k plus 1. So the denominator here is less than the denominator in the expression of AK plus 1. So when we flip them, that's what we have. So now, both conditions of the alternating series test are satisfied. Hence, by the alternating series test, the series conversion. Okay. So it's not hard task really to satisfy. We have to make sure the term goes to 0 and they are actually decreasing. Okay, questions? Now we look quickly at number 17, which was sum of the following type of terms: -1 to the k plus 1, and the k start at 1 to infinity, and this is k squared over k to the power 3 plus 1. Okay. Again, here the ak are absolutely in this time k squared over k to the power 3 plus 1. And now first we have to make sure both conditions are satisfied because it's alternating. Okay. The ak, it means that's the limit of k squared over k to the 3 plus 1. Okay. We divide by k squared both sides. We will have 1 over k plus 1 over k squared. The limit is definitely 0 because this goes to infinity, this goes to 0. The whole thing goes to infinity. 1 over something very large is equal to 0. So first condition is satisfied. Now the second condition, the fact that the ak is decreasing. Okay. Now note that in the first problem, checking that's decreasing easy because we said that the denominator gets larger, so 1 over it is going to become smaller. Here, the numerator, as k increase, the numerator gets larger, the denominator gets larger. So the question is why the term still decrease, even though both are getting larger. So one way to go around the k decrease. So we look at the following function. So we look at the function that at x takes the value x squared over x to the power 3 plus 1. Okay? And we show that this function is decreasing. And to make it easy on us, as I told you yesterday, there are two ways of showing it decreasing. One way is find the derivative, show the derivative negative, or you can graph the function, which is I'm allowing it in those problems. So if we graph it, and we can pick up our calculator and graph it, we're going to realize that this function is actually going to decrease. Eventually going to decrease. If the function decreases, it means if I plug in k for x, f of k is going to be, so if this is k, and this is k plus 1. So f of k, this is ak, and this is ak plus 1. So if the function decreases, definitely the sequence is decreasing. So this is a decreasing function, hence the sequence ak is decreasing. So by the alternating series test, my series converge. Okay. A question before I move on. All right. So number 30, of course, I told you yesterday that you will not be able to do it. So we're gonna, today you should be able to do it. So we're gonna look at number 30 and then the theory kind of behind it, and then we move on. So first, before I do that, I need to talk about the idea of a remainder. Remainder or error usually. Idea is first definition, what's a remainder? Suppose we have a series, and this time doesn't have to be alternating. So it's just any series in general. So A1 plus A2 plus A3, etc., plus AN. So we're adding those terms. So we're adding those terms, that's a series. And let us say that this series converge, meaning that as we add the terms, we get close to a sum, a certain number. So we're going to call it S. So S is the sum of the series. So let us say that the series converge. What does this mean to us? What does it mean? The series converge, it means when I start adding those terms, So it means when n is large, when I start adding the terms, the partial sums Sn become close to S, or S is almost equal to Sn. So to say that the series converge, it means as we start adding the terms, we compute those partial sums become close to its fixed number S. But here's the thing. Suppose, so this is my Sn, the partial sum, and when n is large, those Sn are almost S. But definitely the Sn are not equal to S. They are approximating S. And usually the larger the number of terms we add, the closer we are getting close to S. So when we add, let us say the first 100 numbers, we're not going to get the exact sum. There is a piece that we're not really taking care into consideration. This piece here, the leftover piece, this is called the remainder. Means if we use the first n terms to approximate the sum, there are still terms we haven't taken into consideration. Those terms are called the remainder. So we're going to define a remainder. So the remainder, or sometimes called the error, is defined to be the following. When I use Sn to approximate the sum, how far is Sn from the actual value? So the error is defined to be the actual value of the sum minus the Sn. So let's see, for example, I'm going to work first with a series that we know, and then we talk about 30. So for example, okay, so basically the remainder, it means that suppose I use the first 100 terms to approximate the whole sum. There is an error in the estimation. I mean, I'm not really getting exactly the value. The remainder is basically this error. What's the error obtained when I use the nth partial sum to approximate the whole sum? That's really what the remainder is. So for example, let me take a series that we know. Suppose I take the following series. 1 plus a half plus 1 over 2 squared, something like that. And this is the geometric series, etc., etc., etc. Okay, so that's the geometric series. So let's remember that's geometric, and the ratio is a half. Now the geometric series, we know the sum. It means if we keep adding those terms, the sum is going to be the first term, if you guys remember, times 1 over 1 minus the ratio, which is going to be equal to 1. It means for us, if we keep adding those terms, we should get closer and closer to 1. Now, suppose I evaluate R6. Sorry, I evaluate as 6. So I'm going to write as 6 here. Okay. Suppose I evaluate as 6. It means I add the first 6 terms up to here. So I add the first 6 terms, and I take my calculator and I add them. And I did that myself yesterday. Is you get 0.9843. If you physically add those, it means if you take those sums and you add them, it's 0.9843. So of course, it's very close to the actual value of the sum. I mean, even if you add the first 6 terms, you're getting actually very close to 1. But there is an error. There is those pieces that I didn't add. This is what we're going to call as the remainder. It means, or the error in the approximation. So in this scenario, the remainder, R6, is actually the whole sum minus the sum of the first 3 terms. So it's going to be, if I do the math, 0.0157. Okay, so this is example, shouldn't be equal to 2. Did I do a mistake?
Yeah, wouldn't the sum be 2?
Yes, you're absolutely correct. Let me start at a half. Thank you very much, Elizabeth. Shall I start at a half? Is it okay with you? Okay, I'm going to start at the half just so I don't have to rewrite. If I start at the half, I will be all right. It will be a half times that. And actually, in my notes, I honestly started at the half. That's why I copied this. So, and this is going to become S5, which doesn't really matter at this stage. And this is going to become S5. Thanks, Elizabeth. Thanks, all of you. All right. So I'm just going to take 1, 2, 3, 4, 5. I'm going to add the first 5 terms, and I get that much. So R5 is going to be 1 minus it. So basically, what's going to be, what's the leftover, which is very small. It means that all those terms, all the terms that I didn't really add, all those I didn't add, look how small they are. And that's what really called the remainder. Okay. So in this problem, in this example, I took something that we know everything about. Now, most of the time, we actually don't know the actual sum. And the question is, if I don't know the actual sum, how can I estimate the remainder? So if I don't know the actual sum, can I have still an idea what the sum is equal to? It means when I approximate by those partial sums, can I still know how much the sum is equal to? So this problem, I knew everything. But the second problem is going to be, okay, most of the time, you don't know the sum. Can you still estimate a little bit where the sum is going to be equal to, right? But that's the remainder. That's the idea of the remainder, okay? And the remainder has to be small because the remainder is used to approximate S6 or the partial sum by the total sum. So for alternating series, there is a very nice formula that will help me to find the remainder. So I will state it and then I will use it. Okay. So remainder for alternating series, and this is only true for an alternating series. So suppose we have an alternating series where both conditions of the alternating series test are satisfied. So let sigma ak be an alternating series where the limit of the ak goes to 0 and the ak is decreasing. Both are conditions are satisfied. Under those conditions, the series converge. Let S be the sum. Okay, I'm reading it very carefully, very slowly. Okay, all right. Then the remainder, an absolute value, it means how far is the actual sum, the first partial sum, is less than an plus 1. I explained that very clearly. In other words, the remainder is always less than the absolute value of the first neglected term. So I give you a minute to basically finish writing and then I explain it clearly. Okay. So let's see what does this mean. It means if I have an alternating series where all the conditions are satisfied, it means the ANs goes to 0 and those are decreasing, A1 larger than A2. Then the remainder, so if I use the first n terms, this is Sn, to estimate the whole sum, then there is of course a certain part that I didn't take it. This part here, this remainder here, in absolute value, is actually less than the first term we neglect in the sum. It means it's going to be less than an plus 1. That's what it tells me. It means this whole remainder here is less than this first term that we neglect after Sn. So this really gives us an idea how small this remainder is. All right, so with this in mind, I will do an example to verify this, and then you guys should be ready for number 30. So let us say, take an example. So example is, so this is the best we can get in an alternating series to have an idea what the sum is equal to. So for example, let me consider the following series. Sigma k equal 1 to infinity of -1 to the k plus 1 over k. All right, that's my sum. So if we write it up, we get a 1 for k equal 1. So I will have a 1 minus a half plus a third minus a fourth, and so on and so forth. Okay. Now this series, both conditions of the alternating series test are satisfied. So here my AK is 1 over k. And then we know that the limit of the AK is equal to 0. That's satisfied. And then we know that the sequence AK is decreasing. So both conditions, so it means that the series converges. Okay. So the first question is find S5. Okay, so find S5. It means the sum of the first 5 terms. So it's 1 minus a half plus a third minus a fourth plus a fifth. 1, 2, 3, 4, 5. So if I add those, and of course we add them, just add them, nothing more than that. That's S5. Okay. Now question number 2 is the following. So this is a sum, and I know it converges. So I'm going to rewrite this. So this is my sum. Plus 1 over 5, minus 1 over 6, plus 1 over 7, plus dot, 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 dot. And this converges to a number S. It means as we keep adding, we get close to a number. So my question is, let us say I use the first 5 terms to estimate S, to approximate S. There is an error. What is the error? Okay, so question number 2 is the following. If S5 is used to estimate, so I only use the first 5 terms to estimate the actual sum. There is an error. So if S5 is used to estimate the value of the sum. Find an upper bound on the error produced. It means find what's the maximum value that the error can have. Find an upper bound, that's what they mean, on the error. Okay, that's really the question. It means when I use S5 to estimate the whole sum, there is an error because I am missing on all those. What is the error? Okay, the remainder theorem tells me the following. This series converges. The remainder theorem tells me that this is alternating and both conditions are satisfied because this formula doesn't work for other series. The remainder tells me that S minus S5, it means how far S from the sum of the first is always less than the following. The first term we neglect after S5. The first term we neglect is 1 over 6. Okay, so what it tells me that the error is less than the first term. It means this is less than 1 over 6. So if I use the first 5 terms to estimate the sum, I have an error in the estimate. And the error is less than 1 over 6. That's how the remainder theorem tells me. Now, what is 1 over 6? So it means that S, the total sum, minus S5, which is 0.83861, it means how far those is actually less than 1.6 is 1.6 repeating, basically. That much. So that's really the error. So if I use the first 5 terms, I don't get quite the value. I get the value within the error of 1.666. So intuitively, it means that S minus 0.83. So it means that S minus this, so that's the error. That's the maximum value on the error. That's really what the problem is asking us. But for us, it means that S minus this is somewhere between 0.166 and minus 0.166. That's really what it tells me. So how far S is from the sum of the first 5 terms is somewhere in between. So we have an idea about the sum up to an error of 0.166. So now we can almost, have a feeling for the sum. Now, if I need a better estimate, what shall I do? If I need a better estimate, what shall I do?
Increase the number of terms that you're using for the sum.
Increase the number of terms. So if I use, for example, if I use the first 100 terms in this particular problem, if I use the first 100 terms, and as I showed yesterday, we can compute those very easily. If I use them, my error in this particular problem is going to be less than 1 over 101 because it's less than the first term you neglect after S100. So I have definitely a better estimate. So I can move on, I can estimate it within any accuracy I want. I can estimate it with any accuracy I would like to. And that's the idea of the remainder. Okay, so it's giving me a way to estimate the sum within any given accuracy, actually. Okay. Now, if I have a series where the terms actually are, like if I had, for example, square here, square here, square here, square here, it means the term goes to 0 faster than the 1 over n. I can have a better accuracy for the same number of terms. So if I have like here square, 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 let us say, this is going to be less than 1 over 6 square. So I really get my accuracy at a much, much better. So S5 will better estimate the sum than if I take sigma, the 1 over n, because the terms will go to 0 much faster. So fewer terms are needed to estimate the sum. So that's really the idea of a remainder. But the unfortunate thing that this only works for alternating series. Otherwise, it would have been great. It only works for alternating. It does not hold for other series. Otherwise, I would have given them to you. Okay, so that's really the idea. So it's interesting because it starts making me kind of interact with the sum more. Any questions? Right. And this is number 30, Zach. So you should be able right now to do the number. Okay. Right now we're going to still with the same section, talk about the idea of absolute and conditional conversion. It's a little bit confusing, but all this section is not easy anyway, all this chapter, and conditional conversions. Okay, so absolute and conditional conversions. All right, first I start with the definition and then I will proceed. First, definition. Suppose I have a series and it's not alternating anymore. That's the regular odd series, but the terms are not positive as well. So that's sigma an. As I said yesterday, I don't like the fact that the book using an for alternating and non-alternating, but there isn't much I can do about the book. So be a series. The terms are not necessarily positive anymore. That's any series. The term could be anything. And we say that sigma an is absolutely convergent okay, with that it's absolutely convergent if the series, the following series, sigma, absolute value of the AK, sorry, I use N by not thinking, doesn't matter. Absolute value of the AK, if this series, it means if I take everything in absolute value, converges. Okay, so we have a series, not necessarily of positive terms. We say that it is absolutely convergent if, when I take the series in absolute value, so I don't have any minuses, I get rid of everything called minus, this new series, now I have a new one, it converges. So for example, question is determine if the series below are absolutely convergent or not. So determine if the series are absolutely convergent. Are absolutely convergent. All right. So example, suppose I take the following series. Sigma, let us say, -1 to the k over k squared. Okay, is it absolutely convergent? What does this mean? It means I'm going to take the series and I'm going to put absolute value around the term. That's the series I'm going to look at. To infinity. All right. So if I take the absolute value, what will happen? So watch. Without absolute value, this is, if k is 1, this is going to give me -1 plus 1 over 2 squared. That's without absolute value. And so on and so forth. When I put the absolute value, what does it mean? It means I'm taking everything in absolute value. So if k is 1, I'm going to get a 1 plus 1 over 2 squared plus 1 over 3 squared. So I don't have this minus anymore. Plus 1 over 4 squared, and so on and so forth. Now, is this series convergent? Yes, no, why? Back to you. Does the series converge? Yes, no, and why? If you say yes, you justify. If you say no, you justify.
Yes.
Yes, because. What type of series is that? Look at it very carefully. So if I rewrite it in sigma notation, what type of series I'm going to have? Okay. It's a P series. Exactly, yes, because it's a P series with P equal to 2. Okay, it's a P series with P is equal to 2. Hence, the series converges. Hence, the series is absolutely convergent. Okay, so it's absolutely convergent because when we put the absolute value, we have a convergent series. Okay, now another example. Suppose I take the following series. Sigma -1 to the k plus 1 over k. K starting from 1 to infinity. Okay. And again, so this is, the question is it absolutely convergent? All right, so I'm going to take it in absolute value. So that's what absolute, so I take all the term in absolute value. You know, when we take an absolute value, basically this -1 is disappear because -1, whether it's plus 1 or -1, is going to disappear. So this is going to become actually 1 plus a half plus a third plus a fourth plus etc. Or in sigma notation, this is nothing more than sigma 1 over k, k equal 1 to infinity. Okay, so that's in absolute value. So now the question, is this convergent or divergent?
Divergent.
Absolutely, that's divergent. There's a P series, which is basically the integral test with P equal to 1, which means that the series, this one, is not absolutely convergent. Okay, it's not absolutely convergent. All right. Any questions? So let us look at this series here. Let's look at this one. What's really going on? Let us note something. Note that if I take this series, sigma minus 1 to the k plus 1 over k. Okay, it means this original one, which is 1 minus a half plus a third minus a fourth, etc. Okay, if I take this series, is this series the way it stands, this alternating series, is this conversion? Yes or no? As an alternating series. This series without absolute value, this is the way it looks for you. Does this series converge, yes or not? This one. Forget about the first part for a second.
Yeah,
Because
it's equal to 0, 1 over infinity.
not only that, by which test it converges?
Alternating series test.
What?
Alternating series.
Yes, conversion by the alternating series test. Because, of course, the terms 1 over k goes to 0, and the sequence 1 over k is a decreasing sequence. So this series converge by the alternating series test. However, when I put the absolute value, it diverges. Okay, so without absolute value, it converges. When I put the absolute value, it diverges. I mean, it's not very, very bizarre, because when I don't put the absolute value, what's happening to the sum? You know, we're subtracting something, then we add. So there is some kind of compensation in the sum. We subtract, we add, we subtract, we add, we subtract, we add. So there is a possibility that eventually we get close to a fixed number. With absolute,
question.
yes.
What is the exponent of the -1? Is that
K plus
k
one.
minus 1? K plus
Doesn't
1.
matter whether it's actually even k minus 1 would be also correct. Okay.
Okay.
All right. So this is a series where if I, without absolute value, the original series, it converges by the alternating series test, because we have, as I said, it's a compensation. We add term, then we subtract, then we're going to add a little bit less. Then we take away a little bit less. We add a little bit less. So the alternating series test tells me that this one will converge. Without absolute value, we're just adding 1 plus a half plus a third plus a fourth. This one, the integral test tells me it diverges. Those type of series where with absolute value diverge, without them converge, we call them conditionally convergent. Okay, however, this one is divergent. We say that this series minus 1 to the k plus 1 over k is conditionally convergent. Okay, so let us define the word conditionally convergent. So what does it mean in general for a series to be conditionally convergent? All right, so definition. definition. Okay. A series sigma AK is called a series sigma AK in general is called conditionally convergent if the series itself converge, the series converge, but when I put the absolute value, it diverges. It means it's not absolutely convergent. But when I put the absolute value, this one diverges. Okay, so a series is called conditionally convergent if it converges like this itself, but when I put the absolute value, it diverges. It means the series converges, but not absolutely. So it means the series is convergent, but not absolutely convergent. So that's a new word that we've learned today. So let us take examples of this type of behavior. So for example, okay, for example, suppose I take sigma -1 to the k plus 1 over the square root of k. Okay. What do you think about this series? Is it conditionally convergent, yes or no? So I started with a fairly simple one. Do you think it's conditionally convergent? Yes, anybody else besides Elizabeth?
Convergent.
Is it conditionally? What do I mean? Okay, let's check. What does mean conditionally? It means without absolute value converge. When I put the absolute value diverge. Let's see if this is satisfied. Okay, without absolute value by itself. So this is means 1 minus 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 4, and so on and so forth. Now, does this series converge by itself? Forget about conditionally. Does this series converge? Yes or no, and why? First, what do we notice? First, we notice alternating. Okay. Now, does it satisfy the condition of the alternating series test? If it does, it means it's converged. So let us see here. The terms are 1 over square root of k. These are the terms. So the limit of 1 over the square root of k is equal to 0. First condition satisfied. Second condition, the sequence, those are absolutely decreasing. Because the numerator is increasing, it means 1 over is absolutely decreasing. So it means that the series converge by the alternating series test. Means eventually, if I keep adding, we get to a number, and we know somehow how to estimate the sum. Now, what if I plop in the absolute value? It means if I take this, so the series converge. However, if I take the series and I take the absolute value, means this one I'm going to get 1 plus that plus this, etc. it means I will get this one, 1 over the square root of k. Now, does this one converge or diverge? So when I put the absolute value, what happens? So I took away those minuses. So I start adding them. Does this converge? Yes.
Diverge
Diverge, absolutely, because
because it's a P series and P is equal to 1/2 and it's less than 1.
absolutely correct. It means my series is conditionally convergent. So that's what we call conditionally convergent. Okay, so I plug in the absolute value. You know, when I start, then it diverges, but without them is converged. That's example of a conditionally convergent sequence. Okay. Now there is a theorem that tells me the following. Okay, theorem. Okay, it states that if I have a series sigma an is absolutely convergent. It means when plugging the absolute value, it's convergent, then it's convergent without absolute value. Then it's also convergent. And let me write this in a clearer way. Convergent. That is, if when I plug in the absolute value, if this one converge, then without absolute value, it will also converge. However, so what the theorem tells me that if you have a series and you know it is absolutely convergent, it means you know that when you put the absolute value, it will converge, then without them, it will also converge. But of course, vice versa is not correct. If it converges without absolute value, we have no idea whether it converges with them. Intuition is that if this one converges, it means those terms are going to 0 and they are going to 0 very fast. So even when you remove the absolute value, they will still go to 0 very fast. That's really the intuition behind why this holding. Okay, so now what's the benefit of that? So we're gonna do the following example. Suppose I give you a generic series. Suppose I give you the following series. And I ask you is determine if the series is absolutely convergent, conditionally convergent, or diverges. Okay. All right, so I'm going to give you a series and I'm going to do that. Suppose I take the following sigma. Let me see what I want. I want the following. One to infinity. And the question is it absolutely, conditionally, or diverges? Which condition shall we try first? Shall we try to check if it's convergent? Or shall we try to check whether it's absolutely convergent? Because I have to check.
Shall we try just convergent first to see if it just diverges? We just end the problem there.
Okay, so what do you think we're going to come up with in this particular series? You think it's going to converge? What do you think? All of you.
Most likely going to converge.
Because what type of series is this?
Alternating series.
That's alternating series. Do you think it's going to satisfy the condition of the alternating series test? Not right.
Yes.
Okay, because the terms 1 over k squared plus 1, they go to 0, and they are decreasing, because when k increases, the denominator will increase, making the term increase. So intuitively, it's going to converge. Are we done? I'm just talking. I didn't start on purpose. Are we done?
No.
What we have to do is what? Check if it's convergent in absolute value. Right?
Yes.
So what do you think I'm going to do now? What's the better approach, the fastest approach? I will start with the absolute convergence. If it converges with absolute value, I am done. Because if it converges with absolute value, it will converge without them as well. If it doesn't converge in absolute value, then I will check the conversions. That will be easier. So we start with, it's easier. Because if it's converged absolutely, it means I'm done. I don't have to do anything. Start with absolute conversions. Okay, we start with that. All right. So in absolute conversions, what do we have? We have sigma, everything in absolute value. Means now I am adding the term. Now I have a bunch of positive terms. So this is when I take the absolute value, the minus 1 to the k plus 1 is actually going to become a 1. And this will become 1 over k squared plus k in absolute value. Another question is, does the series converge? Yes or no? Now we have to go back and use the thing we know, all the tests we know. So let me check. Yes, because?
Because wouldn't you say that k squared plus k equals k to the third power and
no.
Oh,
Why did I scream? No. If I was on the board, I would have hit the board in front of you. No.
Yikes, sorry.
No, don't worry about it. Don't worry about it. I wish I had the board in front of me. Okay, how do we even show that this can converge? Keep going. We're going to use the limit comparison test. Okay, the limit comparison test. And I say that for k is large, this is almost like 1 over k squared. Okay, I'm bringing back what we know. These are positive terms. This is bk, and these are my ak. All right, and now I compute the limit of the ak over bk. So, of course, we have to pull things from things we know, otherwise I cannot proceed. So this is going to give me, if I do things correctly, k squared over k squared plus k, which is equal to 1. This is not 0 and not infinity. So limit comparison test is applicable. Okay, since sigma 1 over k squared converges, then sigma 1 over k squared plus k will also converge. Okay, so what do we have here? So it means that when I plug in the absolute value, so it means that this series, when I plug in the absolute value, this one converges. So with the absolute values converge. Hence, the series is absolutely convergent. If it's absolutely convergent, it means when I put the absolute value, it will converge. It means without them, it will also converge. So we don't have to check anything or whatsoever. So convergence has my original series is absolutely convergent. Okay, that I'm done. I'm done. In this particular problem, I'm done. I don't have to go any further because when we add them when we take the absolute value, we add them, it will converge. Even without the absolute value, it will converge. And because the terms are going to zero very fast. So this is absolutely convergent. If at this stage I got divergent, then I will have to check whether it converged without. All right, sorry because I screamed, but I have to make sure that you don't repeat the mistake again. What else I want to say? Okay, that's it for today. Please do the homework. And if you have any difficulties, as usual, we go over them tomorrow. All right, so class is dismissed. Any student with question can remain.